Hello everyone. My objective by end of this presentation is to help you understand how advanced plastic recycling technology can enable cost-effective operations. So let's jump right into the presentation. Before we start the technical presentation, a little bit about myself. I am Suhas Dixit, founder and CEO of APChemi. I am formally trained in chemistry, chemical engineering, marketing, and contract management. I've been inventing technologies since 2007. I've got 12 patents, three patents granted in India, one patent granted in South Africa, and these patents also are going positive examination in Europe and USA. My expertise is pyrolysis of plastic, tire, and biomass, also purification of pyrolysis oil, as well as advanced or chemical recycling of end-of-life plastic waste. About my company, we are APChemi or Agile Process Chemicals. As APChemi, we are leaders in pyrolysis. We turn non-recyclable plastic, tire, and biomass waste into value. These are the visuals of the projects that we have developed and the field in which we are working. We have developed 47 pyrolysis plants since 2007 to process plastic, tire, and biomass. We are supported by Shell Petrochemicals. We recently raised $2.4 million in collaboration with Aalborg University, Denmark, to convert plastic waste and biomass waste into green hydrogen. It's a 3-year research program that we are working with in collaboration with Aalborg University. We are working on global projects of converting plastic, tire, and biomass into high-value products. In Europe, we are working on a 240 metric ton per day pyrolysis plant. Recently, we completed 42 metric ton per day pyrolysis plant engineering assignment planned to be deployed in UK. Projects that we have done till now have generated over 3,000 jobs globally. Recently, we have generated over 7 proof of concept on how you can start with this kind of end of life plastic waste and produce a chemically recycled or advanced recycled projects using this kind of technology and machinery. We offer award-winning solutions to accelerate plastic circularity and decarbonization. We have won Indo-Danish green hydrogen funding call for conversion of plastic into hydrogen. Our technology has been recognized as circular disruptive technology for managing plastic waste. A couple of years ago, we won KPMG's Enrich Award for ready to scale startup. We have an exceptional team. I'm very proud of my team. I have 12 years experience in this domain. Aruna heads operations with um, uh, 10 years experience in Tesco as well as Maersk in operations. Sanam has experience of developing over 50 pyrolysis projects with us. We have right set of advisors, and together as a team of 20, we have 310 years of experience in pyrolysis and oil purification. And we are united by a common vision to engineer plastic circularity. Our team kind of goes beyond our in-house team. We have collaborated across the world with global corporates, academia, as well as leading platforms that are working in the domain of plastic circularity as well as decarbonization. Now let's start with the technical presentation. Now, if we look at what are the different types of plastic waste that are available and what are the different types of technologies that are available for managing this type of plastic waste, this is the slide that you want to look at. So, you must have seen that on the plastic packaging inside a triangle, number 1 to number 7 is written. That signifies which type of plastic is it. So as far as polyethylene terephthalate is considered, globally around 80 to 95% of polyethylene terephthalate gets recycled. Polyethylene terephthalate recycling is not a problem to be solved really. So it gets recycled using chemical recycling. And both technologies like bottle to bottle as well as bottle to fiber technologies also are there to convert waste water bottles or soda bottles into your new bottle, food grade bottle, or production of fiber which is used for making polyester cloth or even cotton and polyester cloth combined can also be produced from PET bottles. Other types of plastics, let us say HDP, PVC, LDP, PP, PS, in case these plastics are segregated, in case of segregated plastic waste, then you can do the downcycling, which is mechanical recycling. You make granules from these plastics, and these granules cannot be used for food and pharma application. It can be used for, let us say, detergent boxes or anything that has nothing to do with food and pharma packaging. For that, mechanical recycling really helps. And almost all this 9% of recycling that is happening, it is all mechanical recycling. Solvolysis is one of the upcycling field which is coming up in case plastic is segregated. Uh, so it's very new at this stage. 99% of plastic waste generated is not recycled. That for that kind because it is mixed. It is like all these polymers are mixed. Yeah. So that's why you don't have separate rows. It's all kind of mixed. And mixed plastic waste, you can do downcycling by compression molding, or in case you have to upcycle, then you can use pyrolysis and pyrolysis oil purification or gasification. So our company deals in pyrolysis and oil purification technology as such. Uh, why do chemical recycling of plastic waste is one of the important question, and the reason for that is that less than 10% of 350 million metric tons of plastic waste is recycled. Rest all plastic waste goes to landfills, environment, and it is burned in incineration plants. So it's a huge problem, and a lot of people don't know this that plastic waste management also generates huge amount of carbon footprint. So amount of plastic waste that is burned in incineration plant and landfill fires generates 300 million metric tons of carbon dioxide every year. So from now to 2030, we will burn additionally 1.2 billion tons of plastic waste, and that will result into 3.5 billion tons of carbon dioxide emission. So it's a plastic waste management has a very huge carbon footprint. So if you see global plastic waste generation, it will increase from around 350 million metric tons per annum to somewhere around 460 million metric tons per annum by 2030. Um, Plastic waste that will go to incineration and landfill fire also will steadily increase to right now around 100 million metric tons to around 150 million metric tons per year. And if you see the chemical recycling ambitions of the top five global polymer producers, that would probably lead to chemical recycling of maybe 10 kilotons per annum of end of life plastic waste. So the ambition for recycling put together the 10 top 10 global polymer producers is very low, and that's why huge amount of plastic waste will keep going to landfills as such. So this, if you have to put all this pictorially, this is how it will look like that the crude oil is used for production of polymers for FMCGs. FMCGs use plastic packaging, and that generates around 350 million metric tons of plastic waste, which generates 300 million metric tons per annum of carbon dioxide emission. Now, even if you take this plastic waste and convert it into plastic oil or pyrolysis oil, this pyrolysis oil has impurities, so it cannot be used back for production of polymers, and that's why there is a dependence on crude oil. So you can see that this is very much a linear economy. It's not a circular economy. So crude oil to polymers to FMCG to plastic dumping or burning. So it's kind of a linear economy. There's no circularity there. And that's because impurities in plastic waste stop the circularity of the carbon in the plastic waste. So the way APChemi technology solves this problem is we can either convert plastic waste into purified pyrolysis oil or a pure oil, which is a very good feedstock to be blended with crude oil naphtha for production of circular polymers, which are food and pharma grade. And this is how we create the plastic circularity. In addition to that, our separate technology also converts plastic into bitumen for road construction. So it captures the carbon from plastic waste into bitumen, in the road so that without not only captures it into road and also without any microplastic pollution. So there is separate technology that we have. We have one more technology that even if plastic is converted into contaminated oil by somebody else, we can purify that oil so that that oil becomes pure oil and it can be blended with naphtha for production of high value food and pharma grade circular plastic. So this is how we upcycle end of life plastic waste into circular pure oil and bitumen. Our core value is conversion of waste or impure oil into purified oil. So our pyrolysis oil purification technology uh, has lower capex, opex, removes more impurities, and has lesser carbon footprint compared to other technologies for purification of pyrolysis oil like distillation, adsorbents, or hydrotreating. Our pyrolysis oil purification technology has high pyrolysis oil purification efficiency. The core problem of this impure oil or even plastic waste is the chlorine impurities. And our technology removes 99.7% of chlorine impurities and very high quantities of nitrogen, bromine, fluorine, oxygen, silica, acidic, metal, and heavy metal impurities. And this is what makes our technology really usable in case of contaminated plastic waste. Like if you have plastic waste with polyethylene terephthalate contamination, PVC contamination, even like multi-layer packaging, all that can be processed through our technology for production of very good quality oil that can be used as a feedstock for production of circular plastics. We have validated our proof of concept and technologies. We have received written letters of intent from 8 global corporates, including BASF Germany, Shell Singapore, Unilever Global, PepsiCo Global, and so on. So it's not, we are not only producing purified pyrolysis oil, we are also creating the much needed cross value chain collaboration between FMCGs and packaging to accelerate plastic circularity. This other technology that we have, as we mentioned, converting end-of-life plastic waste into bitumen. Uh, the advantages of this technology is that this sustainable bitumen produced from end-of-life plastic waste can be blended up to 20% with conventional bitumen. It has negligible contaminants like organic materials, metals, or stone. It has lower carcinogenicity compared to bitumen itself. It reduces emissions compared to conventional bitumen or plastic to fuel or burning of plastic waste. And it does not create microplastic pollution during road wear and tear. So these are the advantages of our plastic to bitumen technology. And if you see the advantages of pyrolysis and oil purification technologies, our technologies are safe, energy self-sufficient. We have a lot of energy recovery that happens in these technologies. Pyrolysis technology, we have done more than 47 projects. We have huge amount of track record of these technologies. 340, 30 and 330 days of uptime is there, and it's a patented technology that also reduces the carbon footprint. We are able to remove impurities from pyrolysis oil as part of our oil purification technology. And this pyrolysis oil purification technology ensures that purified pyrolysis oil can go for production of circular plastics. Our pyrolysis oil purification technology also reduces the use of chemicals for pyrolysis oil purification and thereby also reduces the scope 2 and scope 3 emissions involved in advanced recycling of plastic waste. So looking at the carbon footprint numbers compared to say burning of plastic waste in landfill fire or incineration plants, our technology brings down the carbon footprint by 50 to 75%. Compared to the conventional pyrolysis and purification of pyrolysis oil, our technology is able to get the job done of producing purified pyrolysis oil at around 20 to 30% lesser carbon footprint because we actually reduce the use of chemicals in pyrolysis oil purification. Now, let's look at the market situation and the engagement process that is required for using these advanced recycling technologies for cost efficient recycling of plastic waste. Uh, so it's a sunrise market to begin with. Recycling market based on pyrolysis is expected to grow to $100 billion by 2030. As per McKinsey and Company, legislations are growing profit pool of recycling industry, and pyrolysis itself is expected to contribute $25 billion to profit pool of recycling industry by 2030. There's a $500 million of plastic tax looming over FMCG and packaging, and uh, legislations like, say, European countries across the world are copying European legislations like recycling targets, plastic tax, extended producer responsibility, and this further, boosts this market every year. Now, looking at a global challenge, this is one of the important concept that we need to grasp, is that even though the core of mismanagement of plastic waste, like 99% of mismanagement of plastic waste happens in Asia and Africa put together, still 99% of investments in plastic waste management happen in Europe, USA, Canada, and Australia put together. So there's a huge disconnect between where is the plastic waste management and where is the investments in managing plastic waste. Now, how do we attract investments in advanced recycling of plastic waste? So it requires a cross value chain collaboration, and this cross value chain collaboration has to be between the players that are involved in plastic circularity. So uh, let us say plastic is used by FMCGs, that goes to consumers, then it consumers give the plastic waste to city councils. City councils appoint the material recovery facility contractor for segregation of plastic waste. That segregated plastic waste has to come to plastic pyrolysis plant, and then plastic pyrolysis plant converts plastic into oil. That oil has to be purified, and then purified pyrolysis oil has to go to monomer production. Then monomer producers don't produce polymers usually, so monomer producers hand over the monomers to the polymer producers, and then polymer producer produces the polymers that go to packaging industry, and packaging gives the packaging material to FMCG. So this is the entire value chain wherein collaborations are required across the value chain to make this happen. Now, this might look very complicated because usually in business deals, so many players are not involved. However, this is what is needed, and we are demonstrating it. The earlier we get into these kind of discussion, these kind of industries can be developed. There's a way to build a collaboration, and APChemi, we as a company have developed expertise in building these kind of collaborations. So this is how the engagement process looks like in building such a sustainable plant at a lower capex and opex. So uh, first, we have to come up with an opportunity approach paper that lays down the opportunity, how much plastic waste is generated in a city, what is happening to that plastic waste right now. If we convert it into oil, then where all that oil can go, who all are the stakeholders in the project, and how the project will be developed as well as say installed, commissioned, and operated for how many years. So overall, project life cycle in a way can be it is to be drafted as part of the opportunity approach paper. Some people call it white paper for developing a chemical process plant, but this becomes kind of a first step or the first document, and this is kind of a mother document that guides the project throughout its life cycle. Once you have the opportunity approach paper and understanding of how you are going to approach the opportunity, next step is to develop a proof of concept. Proof of concept means that the you at a commercial scale, you are going to develop a process plant that will take maybe 50 metric tons per day or 100 metric tons per day of plastic waste and convert it into purified oil, which will be used by polymer producers to mix with naphtha and produce circular polymers. So This proof of concept assignment would be kind of start with, say, 30 kilograms of plastic waste rather than 50 tons. Start with 30 kilogram at R&D scale, push it through the technology, and then see how the technology performs to convert that 30 kilogram of plastic waste into purified pyrolysis oil. So basically, proof of concept is involves doing maybe 10-15 R&D scale experiments wherein you not only evaluate the raw material but also combine the raw material with the technology and understand how what value can be created by combining particular raw material and particular technology. And this is very crucial step. You cannot evaluate raw material separately and technology separately. You have to combine them at some point of time, and lowest cost way of doing it is R&D facility. So our R&D facility has equipment worth more than $200,000 where we can conduct experiments of pyrolysis, oil purification, fractional distillation, upgrading, and produce quality of oil that would be acceptable to a petrochemical company for production of monomers and polymers. So once you have proof of concept, then you develop necessary technology performance statement for a given raw material. What would be the yield of the end products, what would be the quality of end products, what would be the quality of emissions, and what would be the quality of those emissions. So once you have developed a technology performance statement at R&D scale, that technology performance statement kind of becomes a backbone for doing say plus or minus 20% capex opex estimation, which is the third stage. Then once you do capex opex estimations, machinery cost estimations, operating cost estimation, land and building estimations, and all, and then you build a financial model. So financial model usually involves like 10-15 years of financial projections, followed by sensitivity analysis. What if the yield goes down? What if the interest rate goes high? So all this financial modeling and sensitivity analysis is done after that. And then you get into engineering and drawing approval. So mainly engineering involves a lot of simulations, like the way we derive process guarantees, warranties, and mechanical performance of equipment guarantee warranties is by doing simulations. Simulation softwares are extremely advanced and they can be used for taking a technology performance statement at an R&D scale, and with a lot of experience that we have of developing these commercial scale plants, we are able to then derive also, say, guarantee warranties for mechanical and process performance at a commercial scale. And once this, the reason why all these steps are mentioned in gray is because that is a de-risking phase. This is where you take out all the risk, and this de-risking usually involves somewhere around 8% of your capital investment. Once your de-risking is complete, then you go into the investment phase where you again do capex opex estimation, which is once engineering is complete, then capex opex estimations are like plus or minus 5-10%. That's where estimates get more accurate. Get into the procurement of equipment, plant installation, pre-commissioning, commissioning, operation, as well as, say, improving operations and growth. So when you follow this entire process over the period of, say, 6 months to 24 months, why 6 to 24 months? Because uh, in certain countries you can get planning permission very quickly. Like in India, usually you get planning permission or pollution control board clearance for setting up chemical process plant within a span of 3 months or so. But sometimes, in countries like Europe and UK or USA, certain regions, it can take 1 year or even 2 year to get permissions. So you have to adjust the speed of the project depending on how much time will it take for entire permitting and all that. But you can do it as quickly as 6 months, or you can do it, it can go up to 24 months depending on location and how quickly permitting can be done. And fundraising also can be done. So you have to adjust the speed of the project. But when you go through this entire detailed process of planning and getting the project up, you can be sure that you would be able to develop a highly competitive, scalable, de-risked and sophisticated project with around 30% lesser capex and opex. And this capex will go up by 30-40% if you don't do proper planning and pilots and proof of concept, de-risking via simulations and all that. So this is where we bring in a lot of strength as a company. So Happy to take questions. This is where you can reach me, and looking forward to collaborating with you on accelerating sustainable circularity of plastic waste. Thank you.